So what we have done so far is, we have looked at how to model consumer behavior. We have looked at, if the economy consists of only consumers, there are no production, how to model that kind of an economy, and what is the concept of equilibrium in that kind of economy, and what is the concept of Pareto efficiency in that kind of economy. Okay, so we have looked at that. Okay, and then we have looked at how to model producers behavior. So after that, a natural thing to do is to understand how to model producers behavior. So that is also that we have done. Okay, and then we have looked at, in a partial equilibrium setting, which is a simple setting, how to define competitive equilibrium. Okay, so now what we are going to do is we'll have an economy where both consumers and producers are there. Okay, so I mean, that's kind of more, I would say, realistic, in the sense that, I mean, usually the production is an important part of economic act. I mean, is an important economic activity, that takes place. Usually the commodities are not available in the consumption form. So you have some inputs and you use that input to convert the commodity into output. Okay, so that is the kind of economy that we would like to model, and we would like to discuss a general equilibrium model, where we have some consumers, some producers. Okay, and we would like to define competitive equilibrium in such a way that all the markets clear simultaneously at some set of prices. Okay, so I mean, of course, the definition of competitive equilibrium is more or less the same. It's demand equal to supply. No matter what kind of model it is, eventually it is just demand equal to supply. Eventually you'll just be solving for demand, you'll just be solving for supply, and then trying to figure out the prices at which the market's clear. Okay, and of course the natural questions that we can ask is, how to find those competitive equilibrium, and are those equilibrium efficient or not? Are markets doing a good job in allocating resources or not? I mean, basically that's a fundamental question. Okay, so if markets are doing a good job in allocating stuff among people, then it's a good thing. Uh, it shows that this is a right way to 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 carry out allocations. Is that okay? Make sense? Okay, so obviously, so we always start the model with something really simple, as simple as it can get. So we want to model a scenario where there is a consumer as well as producer. So how about starting with a scenario where there is just one consumer and one producer? Okay, I mean, so if we can model such a scenario, that really is going to help us get some insights about how to actually model a more complicated economy than this. Is that okay? Fine. So we'll call such a model, where we have one consumer, one producer, or you can say one consumer, one firm. We call such a model Robinson Crusoe economy. Is that okay? Have you understood this? Okay, so let me tell you about Robinson Crusoe economy. So you can imagine that there is an island. Okay, and on that island there is only one person, Robinson Crusoe. Okay, fine, understood. Okay, there is an island. On this island there is only one person, Robinson Crusoe. Okay, so Robinson Crusoe has, let's say, I mean, we can just normalize the time to 1 unit. So Robinson Crusoe has 1 unit of time. You can say 1 day maybe. So 1 full day to allocate to basically gathering coconuts. Okay, or basically enjoying the leisure time on the beach. Is that okay? Fine. So so Robinson Crusoe has one unit of time, you can call it 1 day, and he wants to allocate this day into two activities. One is basically how much time he would like to spend on gathering coconuts, okay, and the remaining time he would spend, okay, on basically leisure activities. Okay, you can say just lying on the beach. Is that okay? Is the model clear? Okay, so you have to keep this story in mind, and using this story I'll just write down the mathematical model for it. Is that okay? Fine. Okay, so let's start. Okay. Robinson Crusoe Economy. Okay, so we have total amount of labor time which is given by 1 unit. By the way, I'm just taking this labor time as 1. It is possible that they in questions, you might see that total amount of labor time available is 24 hours or 365 days, or maybe some other number of hours, maybe some 8 working hours or whatever. So you just have to do that accordingly. Okay, so in the model that I'm specifying here, I'm just treating the total amount of labor time as 1 unit. Is that okay? Fine. Okay, so total amount of time is normalized to 1 unit. Okay, now this Robinson Crusoe, uh, he obviously uh, he likes to consume coconuts. Okay, and he also enjoys leisure time on the beach. Okay, is that fine? So his utility, so we have a utility function of Robinson Crusoe. It's a function of the number of coconuts he consumes and the amount of leisure time he spends on the beach. Is that okay? Fine. So let me just write the utility function. So utility function is a function of CR, okay, where C is the amount of coconuts consumed and R is the leisure time. Okay, so we are going to assume here that coconuts are perfectly divisible. Okay, so we don't have this integer issue. Okay, that it's not that you have to consume in integral quantities. You can also consume any non-negative real quantity. Okay, and leisure is something that you can only basically, because you have only 1 unit of time. Okay, so you cannot go beyond 1 unit of time. So there is a bound on the amount of leisure that you can consume. Is that okay? So you can, if you want to write it, you can say that utility is a function from R plus cross 0, 1 to R. Is that okay? Okay, so notice that this is from 0 to 1 because the amount of time available is 1 unit. Is that clear? Okay. Okay, so we have the utility function. Okay, now there is another thing that we need. We need that if Robinson Crusoe puts L units of time gathering coconuts, how many units of coconuts can he gather? Okay, so we need some relationship between the amount of labor time he puts in to gather coconuts and the amount of coconuts he'll be able to gather by investing that much amount of labor time in gathering coconuts. Is that okay? Fine. So that particular relationship, you can say that that's a production function actually, right? So you put labor in, coconuts out. Is that okay? Fine. So that's a production function. Okay, so we have a production function f, which is a function from R plus 2r plus, okay, and basically, you know, C is equal to f of L. Is that clear? Okay, fine. So this is the utility function of the Robinson Crusoe. This is you know, the relationship between the amount of labor time and the number of coconuts gathered. Okay, so we have consumer, we have firm, and the third thing is basically, you know, it should all be feasible. So what that means is obviously L plus R must be 1. Okay. Okay, so this is actually not the requirement for the model. This is something which will be required for discussing efficiency or competitive equilibrium. Okay, right now if you want you can skip it. For the model, this is all that is required. Is that okay? For describing the model, this is all that is required. Have you all understood this? Okay, okay, okay. So now what we are going to do today is we'll talk about Pareto efficiency. What we'll do tomorrow is we'll talk about competitive equilibrium. Is that okay? Fine. Okay, let's do it. Okay, now just think about it. So just recall the definition of Pareto efficiency. What was the definition of Pareto efficiency? That we say that an allocation is Pareto efficient if there is no feasible way in which you can improve the satisfaction level of one without reducing the satisfaction level of the. Is that okay? Now in this case there is only one person. There is no other, right? So what do you think? How will you define Pareto efficiency in this case?
So just the total possible maximum utility that he can have.
Yeah, so basically you're on right track. So the idea of Pareto efficiency is that you want to choose a feasible allocation that maximizes the utility of the only consumer in this economy, which is Robinson Crusoe. Yes or no? Okay, fine. So that's it. You know, keep this in mind, and I'm just going to write the definition now. Okay, and then we'll solve some problems. Okay. Okay. So remember, in this case, an allocation is how much amount of coconuts is consumed and produced. Okay, how much amount of labor and leisure, how much amount of labor is put into the production activity of the uh, you know of the coconuts. Okay, and how much amount of leisure is consumed by uh, by Robinson Crusoe. Okay, so what I'll say is that an allocation CRL, okay, is let me put star over here. Okay, is said to be Pareto efficient if it solves the following maximization problem. Okay, so let me write the problem that we want this particular allocation to solve. So it should solve the utility maximization problem of Robinson Crusoe. And what is utility maximization problem of Robinson Crusoe? It is to choose, it is basically to pick C, R, and L, okay, such that it maximizes UCR subject to the constraint that C is equal to F of L. Okay, so C must be equal to F of L, and there is one more constraint, that R plus L must be equal to 1. Okay, and of course, non-negativity constraints are also there. So if you want, you can write them. Okay. Okay, so basically, if a problem, I mean, if an allocation solves this particular problem, then it is Pareto efficient. Have you understood this? Okay, so I mean, don't worry so much about it. This is actually nothing but feasible, kind of feasible set. Okay, remember the Edgeworth box in case of pure exchange economy? This is exactly the set of all feasible allocations. So if you just, so basically your job is to choose uh, a feasible allocation that maximizes the utility. What do you need for feasibility in this case? We need that C must be equal to F of L, right? Okay, and we also want R plus L to be 1, right? And of course, all these should be non-negative. So this is nothing but the feasible set. Is that clear to everyone? Okay, good. So how do we solve this? Okay. So what I'm going to do is this. I'll first tell you how to actually. Well, we'll basically pick some model. Okay, we'll pick some problem where I'll specify the utility function and the production function. Okay, and what I'm going to do is this. I'll tell you how to represent those feasible allocations in a graph. Is that okay? And then we'll use the graphical method to solve the problem. Okay, I mean, of course, you can also solve the problem directly without using the graphical method, but obviously looking at the picture always helps, because it makes it very clear, what is going on. Okay, so initially I would strongly recommend to use graphs as much as possible. Later on, of course, when you become really good at it, when you can even imagine your graph in your head, then you can always skip it. Okay, fine. Okay, so let's consider the following situation. So suppose utility function is okay, fine. Okay, and the production function is C equals 3L. Is that fine? Okay, and the total amount of time available in this economy is again 1 unit. Okay, so I mean, of course, so basically you have this allocation problem that you have 1 unit of time. How would you want to allocate this time into leisure and labor activities? Okay, so you want to solve this problem. Okay, but before this, I want to actually see how to solve this, how to actually represent the feasible allocations in a picture. Okay, so what is a feasible allocation here? Okay, so let me first write feasible set. Okay, so feasible allocation is basically any allocation that satisfies all these 3 constraints. Okay, so I'm just going to write it as a set. Okay, so it is C R L in R3 plus, okay, such that C is equal to 3L, okay, R plus L is equal to 1, okay, And yeah, that's it. Is that okay? Fine. These are all feasible allocations. So let's represent them in a picture. Okay. So this is how we can do it. Okay. So this is actually kind of an interesting way to do it. Okay. I'm sure you'll like it. Okay. So let's just do it. Okay. So of course, this is a set in R3 plus. So we cannot use, obviously we don't want to use a three-dimensional picture to do it. Okay, we just want to do it in a two-dimensional setup. So this is an interesting way to do it. Okay, so let me tell you how you can actually do something that is there in 3D in 2D. Okay, so this is the origin of the individual Robinson Crusoe. Okay, and what you can do is you can put firm here. This is the origin of the firm. Okay, fine. Okay, remember, by the way, Edgeworth box, the allocations are actually, subsets in allocations are every allocation is in R4 plus, but we use a two-dimensional picture to do it, right? Okay, so this is also something that even though it's in R3 plus, we can still use a two-dimensional picture to do it. Okay, so let me show you how. It's very interesting. Okay. So you can put, so this is kind of a routine setup, so we can put leisure on horizontal axis, okay, and coconuts on vertical axis. Okay, similarly we can put coconut on vertical axis and labor on horizontal axis. Okay, and let's say this length is 1. Okay, notice that labor plus leisure should be 1. Is that okay? Fine. Now if you look at this point, this is also where L plus R is 1. This point, this is also where L plus R is 1, because if you look at this point, this is the amount of leisure and this is the amount of labor. Is that okay? Because labor is increasing in this direction, leisure is increasing in this direction, exactly the way it happens in Edgeworth box. Yes. Okay, is this clear? Okay, now we have just done this. We still have to also express this, right? C is equal to 3L. So how do we do that? Well, it's just a production function. Just plot the production function. Okay, so let's plot the production function. Is that okay? Yes or no? Right? You can see that as labor increases, the output increases. Yes or no? Okay, now look at any point here. This is a feasible allocation. How is this a feasible allocation? Because C is equal to 3L and L plus R is 1. So the set of feasible allocations is this red line. Have you all understood this? Any questions? Okay, now you want to find efficient allocations. So you want to maximize this subject to the constraint that you want to pick a point on this. So why don't you do this? Let me give you 5 minutes. Solve this problem. basically you want to choose CRL such that you maximize C plus 2R subject to the constraint that CRL is picked from this set. So basically subject to the constraint that you have to pick a point on this red curve. Okay, what is the slope of the indifference curve in this case? Please note that
So
R is on the horizontal axis and
yes,
C
sir.
is on the
It's half. Oh, R is on the horizontal. Yeah,
yeah,
2. Yeah, 2.
2. Okay, 2 in absolute terms, right? Okay. So if it is 2 in absolute terms, and if we plot indifference curves, are they going to be flatter than the production function or steeper than the production function?
Flatter, sir.
Very good. Okay, they'll be flatter. So if I draw an indifference curve from here, for example, do you agree it's going to look like this? Oops. Yes. Do you agree it's going to look like this because it's flatter? Okay. So are you maximizing your utility here?
No, sir.
Very good. Okay. You can do better. Can you do even better?
Yes, sir.
Yes, sir.
This is it, right?
Yes, sir.
So what is Pareto efficient? So what is Pareto efficient allocation?
C star would be 3, L star would be 1, R star would be 0.
L star will be 1 and R star will be 0. Very good.